So section 10.2 is going to be using combinations and the binomial theorem. We're not going to do anything with the binomial theorem. We're going to define it. We're going to talk about something called Pascal's triangle real briefly, actually just in a definition sense. But we're going to focus mostly on combinations. I really want to only focus on the things that I think are really important in this section. And basically from section 1, if you remember, we did something called permutations. So today, combinations for this section is what's different. And really the big important thing on these two sections is understanding the difference between the two. So a combination is a selection of R objects from a group of N objects where the order is not important. So for example, if you remember in the last section, there was problems out of the book and problems that we talked about where you're doing things like a license plate. Well, if you take a collection of, say, 4 letters and 3 numbers and you create a license plate, the order of those was very, very important. You know, if I took 7 random letters and numbers and I rearranged them, that still gives you a distinct license plate. So the order did matter. If we're talking about a combination, we would never want to repeat anything. We would never want to repeat the same combinations of letters and numbers. Okay, so in other words, if you have a random, if you have 4 letters and you spell the word, say, kite. Okay, what we could do with permutations is we could figure out how to rearrange those letters in anything that we want to. So it'd be, say, A, E, K, I, T. It's still using the same 4 letters. These are 2 different permutations, but they are still only one combination because the order is not important. The point is we still have the same 4 letters. So because we have the same 4 letters, that's not 2 different combinations. Combinations are just the number of times that you select something at random with order not mattering. So permutations, that's 2 separate permutations. Combinations, it's the same combination because all the letters are the same. And you're going to see that in a couple of the examples that we do today. Okay, the second thing is called Pascal's triangle. And again, we're not going to really do anything with this. It is kind of a neat thing, but due to time constraints, we're not really going to go into detail with this. It's an arrangement of the values NCR. That's the notation for combinations in a triangular pattern. And then the last thing, the binomial theorem. Again, not something we're going to spend any time on due to time constraints. Binomial theorem is the binomial expansion of A plus B to the n power for any positive integer n. Okay, so let's start talking about these combinations. I want to make sure that we understand this because this isn't something you want to memorize. This is something that you want to understand what you're doing. You want to understand what the question is asking, and then you want to be able to choose wisely whether we're dealing with combinations or permutations. So that's really important. So let's just get into these, and I want to kind of dive into these questions and kind of talk about exactly how this is going to work. So if you read this, it says in lesson 10.1 you learn that order is important for some counting problems. For other counting problems, order is not important. That's exactly what I just got done talking about with what combinations are. So you need to know this formula right here. So you see this is a combination. The C represents combination. This is still n choose R. So that means we have n objects or n things, and we're choosing R of them. So maybe we have 20 total objects and we're going to choose 5 of them. Okay? And this is how it's set up. So essentially what this looks like is we have, if I give you a number, say 3, actually let me give you a bigger number than that, 5C2. So 5 choose 2. The way this is going to be set up is like this. The 5 will be factorial on top, and then down on the bottom will literally be the difference of 5 and 2 and what's left of it. So the 2 numbers on the bottom should add up to be the number on the top. So that's essentially what we have is the difference between the 2, 3 factorial divided by 2 factorial, and you'll actually get an answer there. Okay, so what I want you guys to do is do these ones on your own, and go ahead and hit play when you're ready. Let's make sure that you understand how to set these up and get the answers. So use a calculator to multiply those out and see what you get. Hit play when you're ready. All right, so hopefully you got 35 for the first one. 7 factorial over 4 factorial times 3 factorial. Second one you should have gotten 4. That's 4 factorial over 3 factorial times 1 factorial. Okay, so let's move on to the actual story problem. This is where it gets more interesting and more relevant. So it says you're picking 7 books from a stack of 32. If the order of the books you choose is not important. So here is the most important part of this problem. Because it's telling you that it's not important. When you do problems, typically it will tell you whether it's important or not, or the situation you need to ask yourself whether order is important or not. If it's not, then you will always set it up as a combination. So that's what you want to remember, that's what you want to pay attention to, is whether they're telling you if order matters or not. So because they're saying order is not important, we're going to use combinations. So it sets up like this: 32 objects, choosing 7 of them. That's why I say 32 choose 7. So that means we have 32 on the top. We do 32 minus 7 is 25, and then we have 7. So you have 32 factorial on top, you have 25 factorial and 7 factorial on the bottom, and that gives you a total of 3,365,856 combinations where order does not matter. If we did a permutations, then it would be a lot higher. Okay? So what I want you to do is, in your own words, explain the difference between permutations and combinations. Just write in your own words. Just maybe something that's going to help you in the future. So let's move on. You can pause this if you need to, and then write that, and then kind of just make sure it's part of your notes. Okay, so let's get to the back side of this. So these are a little bit different. They're the same idea, but just different types of problems. So a couple different things we need to look at. So I want to read through this problem with you. It says a standard deck of 52 playing cards has 4 suits with 13 different cards, and you see all of your playing cards listed here. So we want to do 2 things. It says if the order in which the cards are dealt is not important. Again, it's very clear. It says it's not important, so you know you're going to use combinations. So it says how many different 5-card hands are possible. Well, it's pretty much the same thing as what we did before. We set it up as 52 choose 5. 52 total cards, we're choosing 5 of them. So we set it up as the same combination formula as before. 52 on top, minus the 5, you get 47. So you have 47 and 5 on the bottom. And then you multiply that out, and you get 2,598,960. Okay, so that one's the easy one. Okay, that's what we did on the front side of the notes as well. The bottom one's a little bit different. It says, in how many 5-card hands are all 5 cards the same color? Well, these ones are a little bit different because we have 2 different things going on here. Not only are we picking 5 cards, but we need to make sure first that we're picking the right color. So what you do is, because we have 2 different colors, you first need to set up a combination that says this: 2 colors, choosing 1. So that's the first thing that you have to do, because we only want 1 color. So we start with this: two colors to choose from. We're choosing 1 of those colors. Then what we do is we multiply our next. So this is the first event, is first getting the color to be the same, either black or red. 2 choose 1. The second one now is we need 5 cards. How many do we have to choose from? We don't have 52 anymore. Because we're down to 1 color, we now only have 26. So that means we have 26 total items, and we're going to choose 5 of those. That's how they get this down here, the 2 choose 1 and the 26 choose 5. We had to choose our color out of the 2 colors, and then we're choosing the 5 cards out of the 26 cards that we have to choose from. Okay? Remember, it's only 26 because there's only 26 reds and there's only 26 blacks. So when you multiply that all out, you get 131,560. Again, the arithmetic and multiplying it out, I don't need to show you that. That part's pretty easy. It's getting this set up correctly. Okay, what I want you guys to do is go ahead and do these 2 on your own, and then hit play when you're ready. These are almost exactly the same as A and B over here, so refer back to this example to do this, and then see if you can get this. All right, great. Hit play when you're ready. All right, so you guys have, hopefully you got 210 for A. We have 10 choose 4, so we have 10 total books. We're just choosing 4. The order does not matter, so therefore we're using combinations. We have 10 factorial over 6 factorial times 4 factorial. You should get 210. The second one is more like B over here. How many groups of 4 books are all the books either nonfiction or fiction? So the thing is we first have to choose fiction or nonfiction. We have two to choose from. We only want to choose one or the other, fiction or nonfiction. Once we have that, we only have 5 books in each. Okay, so 5 books to choose from in fiction or nonfiction, and we are choosing 4 of them. Okay, so that's how we have the 2 separate ones. 2 types of book, choosing 1, and then the number of that type of book, choosing 4 of them. You should have gotten an answer of 10. Okay, moving on down through the rest of this. So multiple events, which is what we just did in part B above. It says when finding the number of ways both an event A and an event B can happen, you need to multiply as in part B above. When finding the number of ways that an event A or event B can occur, you add. So this above was an and. Both were going to occur. What we need to be able to decide is whether it's an event that is an and or it's an or. One or the other or both of them. So in this bottom one, let's just go through this. We are dealing with William Shakespeare wrote 38 plays, and it can be divided into 3 types. So of the 38 plays, 18 are comedies, 10 are histories, and 10 are tragedies. So we have 3 separate types of plays. So it says how many different sets of exactly 2 comedies and 1 tragedy can you read? Well, because it's an exactly, because they're telling us exactly, we need to make sure that is an and. That means exactly 2 comedies and 1 tragedy. So there's no or about that. So what we need to do then is we're just going to deal with the comedies and the tragedy. So we have 18 comedies. So we write that as 18 choose 2 because we want 2 of them. So there's 18 comedies. We're going to choose 2 of them. And because it's an and, we will multiply by the tragedy. So we have 10 tragedies. So we have 10 to choose from. And we're only going to choose 1 of them. So that's how we set this one up. And we actually get an answer of 1530. Okay, the second one, it says how many different sets of at most 3 plays can you read? So in this one, it's different because it's an or. We don't need 1, 2, 3, or 4, or 0. We only need at most. So it can be 0 plays, it can be 1 play, or it can be 2. And notice how there's an or there. 0, 1, 2, or 3. So what we do then is we take the total number of plays, which is 38, and that's what we have our total as. So we can choose 0, that's one of them. Or, that's a plus. We have 38 choose 1, or 38 choose 2, or 38 choose 3, equals, and then basically we just have our numbers and add them up. So the ors will be added. Okay, so let's look at these examples over here. I'm not going to have you do these on your own because you don't have a calculator with you, and that could be pretty tough. So Student Senate consists of 6 seniors, 5 juniors, 4 sophomores, and 3 freshmen. How many different committees of exactly 2 seniors and 2 juniors can be chosen? Because it's exactly and it's an and, we're just going to deal with the seniors and juniors. We have 6 seniors to choose from, so this will be 6 C, and we want to choose 2 of them, times, we have 5 juniors, so it'll be 5 C 2. We combine those together, we set those up, that will be 6 factorial, sorry for the bell, we have 6 factorial over 4 factorial, 2 factorial, and then 5 factorial over 3 factorial, 2 factorial, and when you multiply that out, you should get 150. Okay, and then the last one, this is more like the second one. It says how many different committees of at most 4 students can be chosen. So that means 0, 1, 2, 3, or 4. So these are all added. So we want to make sure that we add them instead. So this is all of them. So we have the total number of 18 people. So therefore we have 18 to choose from, and we can choose 0, plus, we can choose 1, plus, we can choose 2, plus, we can choose 3, and plus, we can choose 4. So you figure out all of those separately, and then you add them up, and you should get 1 plus 18 plus 153 plus 816 plus 3060, and you should get a grand total of 4,048. So again, you have 2 examples of each of those to hopefully help you through that. Again, your big thing is decide permutation or combination, and then in these ones you're deciding whether it's an and or if it's an or. If it's an and, you multiply. If it's an or, you add. Okay, so bring questions tomorrow. Take your quiz.